Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 5th, 2026, just 4 days ago. It introduces a unified architecture that bridges semantic reasoning with physical dynamics, achieving a 14.5% improvement in daily tasks and up to a 73% boost in dynamic settings. The paper is titled InternVLA-A1, Unifying Understanding, Generation and Action for Robotic Manipulation. And as we'll see later, the implications for handling complex moving environments are really quite significant. Alright, Figure 1 maps out the core architecture. The central row illustrates the three-stage process using a conveyor belt example. First, the understanding expert on the left identifies the object, labeled here as an engine cover. Next, the generation expert predicts its dynamics, essentially visualizing where the cover will slide to in the future. Finally, the action expert on the right executes the precise movement needed to grab it. Surrounding these, the top and bottom rows display the mix of synthetic and real-world scenarios used for training. While the previous figures sketch the high-level concept, Figure 2 details the internal framework of InternVLA-A1. It is divided into 3 vertical columns representing the specialized experts. On the left, the understanding expert encodes images and text instructions to capture the scene context. In the middle, the generation expert uses that context to predict future visual states, effectively imagining the task dynamics. Finally, on the right, the action expert applies flow matching to transform noisy inputs into a smooth, denoised control trajectory. All 3 components are synchronized by the unified masked self-attention layer running across the center. So, having seen the architecture, Table 1 breaks down the specific model configurations. The table lists 2 variants: the smaller intern versus LAA1-2B in the top row, and the larger 3B version below it. The columns reveal that the understanding expert, utilizing either intern versus L3 or QN3VL, accounts for the majority of parameters in both cases. Interestingly, looking at the far right column, both models maintain an inference speed of roughly 13 Hz, because the smaller model's parameter efficiency is offset by its need for higher input resolution. Alright. Shifting from the architecture to the training strategy, Figure 3 presents the hierarchical data pyramid. The foundation at the bottom consists of massive open-source demonstration data, which establishes broad generalizability. The middle layer adds simulated synthetic data, specifically from InternVLA-A1, to introduce diverse physical scenarios that might be rare in reality. Finally, the peak features specialized real-world data. This structure ensures the model learns robust fundamentals from the large base layers before fine-tuning for precise, real-world execution at the top. So, following that training breakdown, Table 4 reports the results on 10 real-world tasks. The first column lists the contenders, comparing baselines like Pi0 against the intern versus LA variants. The data highlights huge gains in dexterity, with the 3 billion parameter model hitting 73% on zip bag and over 90% on make sandwich. Looking at the final average in the bottom right, it achieves 75% overall, and notably, even the smaller 2B model beats the larger Pi0 baseline. Okay, moving from static tasks to dynamic challenges, Figure 6 compares performance on 2 specialized benchmarks. On the left, for express sorting, the lighter bars show that baselines like Pi0 and GrootN 1.5 struggle to break 40%. However, looking at in-motion ingredient picking on the right, the difference is even starker. Here, the red bar reveals that the 3B model achieves 93% success, effectively crushing the baselines, which are stuck at just 20%. Well, to pinpoint the source of these gains, Figure 8 presents an ablation study specifically on the generation expert. The chart compares the standard model in dark pink against a version stripped of its generation module, shown in light pink. The leftmost bars reveal the overall impact. Without the ability to predict future states, the average success rate plunges from 77% to roughly 58%. This gap is even wider for complex tasks, like ingredient picking on the bottom row, proving that the model's imagination is vital for handling dynamic physical interactions. Wrapping up, 2 takeaways stand out. First, integrating a generation expert allows robots to foresee physical dynamics rather than just reacting to them. Second, this predictive capability unlocks massive gains in dynamic environments, suggesting that unified world modeling is the future for generalist robots. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.